Hi everyone, let's discuss the greatest integer or floor function. Basically, this function rounds down. Here's f of x equals the greatest integer of x or the floor of x. The result, the output, is the greatest integer that is not greater than x. I think of this as the Price is Right function after the old game show. If x is the actual price of the item up for bids, then the output of this function, the function value, is the best integer bid you can make that's closest to the actual price of the item up for bids without going over the price. Think rounding down. So for example, try to figure out what these values are. The greatest integer, or the floor of, 2.9 for 3, and for negative 1.1. All right. Now, it's the same function, so we get the same outputs. The greatest integer and floor, they mean the same thing. So if you round down 2.9, you get 2. You don't round off, you round down. I know it rounds off to 3, but you round down to 2. If you round down 3, well, you get 3 itself. If you round down any integer, you get the integer itself. Now, this is where a lot of people mess up. If you round down negative 1.1, remember, you're rounding down, not rounding off. This is a lot like the 2.9, actually. If you round down negative 1.1, you go all the way down to negative 2. There's a way of looking at this. So let's say that x is the number that you're taking the floor of. The result, the output of the function, is the greatest integer, the integer furthest to the right, that is not to the right of x itself. It does not go over. It's the integer that's furthest to the right. It's the greatest integer without going over, without going to the right of x. So for example, for 2.9, even though 3 is a lot closer than 2, the 3 goes over. So you don't want the 3. The 3 goes over. You do not want the 3. You want the 2. It's the greatest integer to the left of 2.9. Or more precisely, it's the greatest integer that is not to the right of 2.9. Because look at our next example. What if x is 3 itself? Well, the greatest integer that does not go over is 3 itself. The greatest integer, or floor, of any integer is itself. Now here's the tricky one. Negative 1.1. Here's negative 2. Here's negative 1. The greatest integer without going over. The negative 1 goes over. We don't want them. The negative 2 is the greatest integer, is the integer furthest to the right that does not go over. Negative 1 is the next integer, and it goes over. So negative 1.1 rounds down to negative 2. This function is often used in computer science applications, like in programming. There's also a ceiling function where you round up, but I won't discuss that. The graph of this is very interesting. It's a staircase graph. It's a staircase graph with a lot of jump discontinuities. In fact, infinitely many jump discontinuities. But this function and this graph is often studied in the first chapter of a calculus book because you talk about ideas of limits and continuity. We have infinitely many jump discontinuities at the integers, the integer values of x. So for example, at x equals 2, the left-hand limit is 1, but the right-hand limit is 2. The fact that the left-hand and right-hand limits mismatch, they exist, but they mismatch, it means there's a jump discontinuity at x equals 2. So for example, if the item up for bids is actually $2 or $2.10 or $2.25 or $2.50, $2.50, or $2.99. What is your best integer bid if you're playing The Price is Right? If you round down 2 or 2.1 or 2.99, you get 2, which explains why you get this flat piece here. If the item up for bids is worth $2, if you round down 2, you get 2. Your best bid is $2. If the item is worth $2.10, $2.20, even $2.99, your best bid is still $2. If you round down 2.99, it's still 2. Now, if you round down 3, you get 3 itself. So you jump up to here. So again, you often see this graph in the first chapter of a calculus book, Issues of Limits and Continuity. But keep this kind of staircase graph in mind. Now, the remainder of these notes are optional. If you're serious about previewing calculus, you should skim over these notes. I introduce ideas of limits and continuity formally in this part. So for example, if you want to know the limit of a function as x approaches 2 from the left, for example, that's the notation, you can consider what happens at x equals 1.9, 1.99, and so forth. Same thing for right-hand limits. You can look at 2.01, 2.001, and so forth. Lots of arrows you can draw. So I talk about limits, like the idea that as x approaches 1 from the left, the function values, the x squared values, approach 1 from below. That was the function we talked about earlier, where you can plug in x equals 0.9, x equals 0.99. The function rule x squared applied, and the y coordinates approached 1, even though the 0.11 was never achieved by that piece of parabola itself. There's an open endpoint there. So the left-hand limit as x approaches 1 is 1, but the 0.11 is not on the graph. When do you have continuity? Well, it's when, let's say at x equals 0, right? Why is there continuity at x equals 0 for the absolute value function? Because the left-hand limit exists, it's 0. The right-hand limit exists, it's 0. And the left-hand limit equals the right-hand limit. They both happen to equal 0. And the function value is 0. The limit value equals the function value. That's when you have continuity. Continuity means basically that the limit value exists and equals the function value, which also exists. In this case, the limit value and the function value is 0. There are 3 types of discontinuities you talk about in calculus: removable discontinuities, or holes, like in this previous example we talked about, whether there's a moon there or not; jump discontinuities, like in these graphs; and infinite discontinuities, like, for example, for y equals 1 over x. That's really messed up. There's no way of fixing that. Next up, more ways of combining functions.